In this course, we're going to be talking about logic and its use cases in electrical engineering. And to dive into that, we need to pick up on one of the videos from the basics of electrical engineering courses. And that's where we introduced logic gates. We had three simple gates. The first was an AND gate, the second was an OR gate, and the last was a NOT gate or an inverter. On the left of each of these gates, we have inputs A and B, or in the case of the inverter, just A. And on the output, that is where we have F. Now we can look at all the possible combinations for the inputs A and B. So for the AND gate, we'd have 0, 0, 0, 1, 1, 0, 1, 1, where 0 corresponds to a low-level logic and 1 corresponds to a high-level logic. Now for the AND gate, the output is only high or a 1 if both A and B are also high. Following the same table for the OR gate output is high if A or B or a combination of A and B are high. And for the inverter, the output is the opposite of the input. So when the input is low, the output's high. And when the input is high, the output is low. Now this course, we're going to be mainly concerned with the binary system, where we have a 0 representing a low signal, 0 volts, and a 1 representing a high signal, or 5 volts. So in this course, simply concerned with digital systems. And in these digital systems, they can be classified into two systems that we're concerned with. The first being combinational logic, where we don't care about the past inputs, and sequential logic, where we do care about the past inputs, and we'll get into that a little bit later. But for now, we really just want to concern ourselves with base numbers. So we're all used to base 10. That's commonly what's taught in school. Perhaps you've been introduced to base 2, and that is where we have two values, 0 or 1, and that is our binary system. There's also base 8, where we have 8 values, 0 to 7. That is our octal system. And lastly, we have our base 16 system, which is our hexadecimal system, or hex. We have 16 values, and we range from 0 to 9, and then we start from A, B, C, D, E, and F to take place of the other values in the system. Now to convert to base 10 from another base, in general, we follow this formula, where if we have some number of some base q given by these terms an all the way to a0, to convert to base 10, we simply take the formula, where this number in base 10 is equal to that base q, the nth power, times that first term, plus q to the n minus 1, times that second term all the way down until we get to that last term. And then we have q raised to the 0, which is simply just 1. Now it's okay if this looks a little bit confusing, because we're going to go through some examples to define what all of these terms are. So if we look at the example of converting a base 2 number to a base 10 number, let that base 2 number be 1101. We simply know that q is equal to 2, because that's our base. Our first term is 1, our second term is 1, third term is 0, and our last term is 1. Now if we look back up here, we can see that the last term is going to be set equal to a naught. So we can set that last term a n minus 3, which is equal to 1. That's going to be equal to that a naught term. And then setting n minus 3 equal to 0, we simply get that n is equal to 3. So now we have everything defined to plug into this formula. So if we want to expand this number in base 2 in terms of base 10, we take q, raise it to the n, which in our case is equal to 3, times that first value right here, which is 1, then plus 2 to the second, because we have an n minus 1 here, and then that second term is also 1. We can follow that through. We can simply expand that to be 8 plus 4 plus 0 plus 1, and that's equal to 13. So then we can finally express that 1101 base 2 is equal to 13 base 10. So now we want to look at an octal number, base 8, and convert it to a base 10. So our octal number is going to be 17. From this, we know that q is equal to 8. The first term is equal to 1. The second term is equal to 7. So 17 base 8 is equal to 15 base 10. Now, if we didn't have bases here, and you simply put 17 is equal to 15, that kind of gets a little bit confusing. Doesn't really make sense, so that's why we include these bases here. Now moving on to a hex example, we are going to convert the number or the value 9a1 base 16 to base 10. So from this, q is equal to 16. That first term is equal to 9. The second term is equal to a. The third term is equal to 1. And again, we can say that n is equal to 2 from this expression here. So if we use the previous formula, we simply end up that expressed in base 10, we have 16 squared times 9 plus 16 to the first times a plus 16 to the 0 power times 1. The question is, how do you even do 16 raised to the first power times a? And this is where we need to look back here, where in this hex value here, this a would be represented by a 10 because it would follow the 9. So then this a simply becomes a 10. And then we can say in base 10, that is equal to 16 squared times 9 plus 16 to the first times 10, 16 to the 0 times 1. And that's going to be equal to 2465. So what if we want to convert back to base 10? For that, we're going to look at an example where we're going to consider in base 10 the number 165, and we want to see what that number is in base 2 or binary. So to do that, what we can do is divide 165 by the base that we're looking for. So in this case, it's 2, which is equal to 82.5. But we are going to concern ourselves in a different manner, where we are going to call this 82 remainder 1. What we're going to do from that is take this 82, divide it by that base again, and that's going to give us 41, or 41 remainder 0. And we can keep following through to get our remainders until we get all the way down to where we get a 0 value, remainder 1, or 0, remainder 0. And what we're going to do is trace our way back up this ladder, but each of these terms, these 1s and 0s, that is the order that we are going to write our number. So from this, we simply have 1, 0, 1 going up the ladder, 0, 0, 1, 0, 1. That is going to be our base 2 number to express 165 in base 10. We can look at a second example where we're using the same number in base 10, 165, and we want the equivalent in hex. So we take 165 divided by the base of 16, that's equal to 10, remainder 5. We take this value 10, divide that by 16, and we get 0, remainder 10. And because we're at that 0 point, we stop. Now looking back up the ladder, you can see that we have a 10 and a 5. But recall that that 10 in hex would become an A. So now going back up the ladder, we would have A and then 5. So our 165 base 10 would be equal to A5 base 16. So notice in these two examples, we went from a binary number, we used the decimal equivalent, and then we were able to convert to hex as well. Now, what if we want to go from base 2 to base 16, because we don't always just want to convert to decimal, and then from decimal to hex, or vice versa. So if we have a number and it's given in binary, so 1010, 0101, to convert to hex, we can group it in sections of 4, and we take the decimal equivalent of each of these 4 numbers. So in this case, this is 10 base 10, and the second grouping is 5 base 10. Now the 10th place in base 16, which is what we're looking for, is represented by A, and the 5th place in base 16 is represented as 5. So from this, we just tie these two together. What we get is A5, which, looking above, we had our binary number, and we jumped over the decimal conversion, kind of, and we arrived at that hex conversion. Now this method can be a little bit confusing, so if you want to convert to decimal, to do any of the conversions from any base, that's always a safe approach.